way, because usually ammonia, when seeding together with the pulverized coal, the ammonia is a gas fuel, right? It will force to ignite before the coal particles. The flame will heat the coal particle, improve the water evaporation as well as the devolatilization process. That means will speed up the ignition of the coal particle. The second way is when those flames, they can consume the oxygen around those coal particles, so that will be extend the burning out time of the char. That means it became more difficult to burn out, so that pose some challenges. The industry always do some how to say advance something we want to try, like a Japanese company, they want to burn 20% ammonia in those big furnace coal-fired power station. The Chinese company like Longyuan Yantai, they burn this industry burn furnace, and the Anhui Tongling, they in the 300 megawatt coal power station, they fired maximum 35% of those ammonia, but just running for 2 hours. That's too short time to see the real ignition and burn out the other things. So in my topic, I will show some works in the recent several years. We worked and in both fundamental and co-firing with coal, some works I will introduce. So for the laminar flame speed, it's very important parameters can be, how to say, compare validation, the chemical kinetics mechanism. So the typical way is people usually use those these kind of spatial expanding bomb method to measurement the speed of those flame speed. But for low speed ammonia, it's better because ammonia flame speed is very low because we're on the ground. We are influenced by the buoyancy. So you will see at the low speed, the ball was lift off. So they are far from the center. So if you decide the diameter changing, there will be some arrows, whatever. Then during the collaboration with Professor Konow from Lund University, the burner was invented in early 2000 from Philip de Gaulle in Eindhoven. The burner has advantage that it's one-dimensional adiabatic. So they use external water thermostatic to compensate the heat loss from the flame to the environment. So through those line fitting, we can always find some velocity with the parameter c equal to 0. It's inter correction, so that means the arrows was quite low. Then it have this advantage because if the flame speed was too high, they will causing some problem and stability. But the advantage is quite suitable for measurement those low speed, especially for ammonia. Then when we come back, we do some modification and update. One way is important thing is original the hole they drilled is 0.5 millimeter, insert 2 thermocouples inside. It's very difficult challenge. And in order to improve the performance later, we find some solution to make those holes small to 0.3 millimeter. Still insert 2 thermocouple lines. So that's quite difficult. The other thing is we build this high pressure rig. We put this heat flux burner into this high pressure rig. Then we can obtain some high pressure data. That's quite good. So you can see the changing original design is this. We want to use this structure to hold this plate. Then we found this difficult with blocking some lasers. So we make this changing the head configuration, as well as the small structure to overcome those cellular flame to improve the performance. Then for the ammonia, if we use a typical water thermostatic, because due to still there was buoyancy, the ammonia flame is quite low speed. So you can see the flame is not really flat one. Then we switched to oil thermostatic. Oil heating, they can have around 300 degrees C, something like that, a little bit lower. You can see the flame was much attached to the surface, so that the thermocouple can have a good performance to measurement the temperature distribution. So the high pressure rig, you can see it can handling a maximum 50 bar. We build by we designed by ourselves and find some company to help to build this one. The ignition, the control system, all developed by our students. You can see this is the figure comparison. The top two is without oil. Without oil, we're all heating. This is the bottom two image is with high temperature oil thermostatic. You can see the flame is quite perfect 1D platform. Then we obtain those kind of data for ammonia air. You can see the data good performance from those from a lean to the rich side. Then we mix with methane because it improve the reaction performance. The typical way is mix with methane, mix with hydrogen. The lack of the data is with the high pressure one, so we put a high pressure rig. We testing the 1 bar, 3 bar, 5 bar. We got those kind of different kind of experimental data, and then some parameter fitting, as well as the pressure fitting, the beta can be obtained. Those kind of data can be validated for your developed mechanism. As well as the syngas. In the original, we think, oh, maybe for biomass gasification, you got so many syngas. The syngas maybe also can good way to replace methane. So we mix the ammonia with syngas. Most composition is hydrogen, and the X-ray is mixing ratio of ammonia with those kind of syngas. You can see most time the line shape looks like this because ammonia is quite low flame speed. Increase this one, we reduce one. We reduce the lambda flame speed, but just except the carbon monoxide. You can see the carbon monoxide, the line shape is quite different. First increasing and then decrease. We further analyze. We're thinking maybe that due to the main way about carbon monoxide is following this reaction with OH radicals. Because if you do not have water or OH radicals in the system, the oxidation of carbon monoxide will be quite difficult. If you first increase adding some ammonia, they will introduce quite a lot of H radicals. Those H radicals will help generation quite an amount of OH. Those OH can help the oxidation of carbon monoxide. Then if the amount exceeds some barrier, then the total performance will be decreased. The other thing is we compare with ammonia with methane, with hydrogen, with different kind of pressure. You can see the total performance. Ethanol, methanol could be also generated from those kind of biomass, could be also zero carbon fuel. So we test with ammonia mixed with kind of methanol, ethanol. Then you have different data. The thing is, what's the relationship between those kind of different fuels? If you just put those molar fractions, you see, different fuel have quite different performance. Then we try to thinking, we normalize those fuel with energy. We can see most of those kind of fuel following the same tendency, just except hydrogen. Hydrogen is this line. The other line you see is quite similar. Then based on those experiment data, we try to develop some mechanism. I think Xin Han did a good job, and Professor Konov also gave us great support. The early ammonia-based mechanism are mostly used to describe the fuel NOx formation, but in the later one, we need to consider more those kind of oxidation and the NOx formation. So then in the year 2020, I guess, we combine this mechanism with syngas mechanism from ELTE, C1 from C4 mechanism from Santiago's mechanism and Professor Konov's mechanism, and update some ammonia sub-mechanism. There was some tables. You can see some different kind of mechanism. They are validate both flame speed, ignition daily time, as well as species distribution. So just recently, the lab ELTE from Hungary, they published a paper with CR. They gave an evaluation about those current mechanism. So you can see the mechanism first version was published in 2020. In that time was Xinlu Han's work. So you can see is in the top 2 performance. Then later we think we should name those mechanisms. So we gave the name of the mechanism called the CEO mechanism. So we later update 1 or 2 version. So just recently, the ELT, they gave evaluation. See our CEO mechanism in the 2022, the latest version, was the best performance to both cover the high pressure and wide equilibrium ratio. So what we do, we update is the mechanism. This is our mechanism. This mechanism from Sharissa, from UCSD. So you can the different is mainly from this part N2 H3, as well as from the NaH to generation the nitrogen. We updated the parameters, so then they have a quite good performance. Then we give a validation from both laminar flame speed from methane mixed with ammonia with 1 pressure, 3 pressure, 1 bar, 3 bar, 5 bar mixed with different kind of hydrogen syngas. This is ignition daily time. We compare with different data because ignition daily time usually is obtained from a shock tube or some different type of experimental. As well as those kind of mixed with different ethanol, methanol. So you can see it's good. From the lean side, from the kinetic simulation, we can see we can reduce the emission of NOx. NOx mainly is NO2, but in some amount of N2O. We need to avoid those, especially those N2O. So you can see with the rich side, we can use those type of stage combustion strategy. First with rage around 0.2 to 1.4, this kind of raging to both reduce the NO emission as well to control the unburned leakage of ammonia. Then I have talking something about mixing with the coal, because coal is quite important in China. So first we invented this, we introduced this Haken type of burner. This is some diffusion flame. In the center, there was a tube. We can inject some coal particles, polarized coal particles. So you can see this image. This is a photo. What we do is we put one continuous laser, like this laser beam. It's a continuous one. If one coal particle coming out from the jet, they will block those lasers. So at the PD here, they will generate a signal. We will use this signal. We can trigger to open the camera. So with ICD camera, we can put those filters. For example, like 430. This one is emissions from CH. CH just coming out from the coal because ammonia doesn't have a carbon, right? Then we can continuous exposure. For example, every 4 milliseconds, explosion 1, open the gate. So you can continue to capture this fluorescence about the same coal particles. So with this one, we can capture the ignition daily time. So this general photos we can take from a normal camera. This is from a nitrogen in the to blow out those particles. This is when replaced with ammonia. You can see the light was seems enhanced. And then we compare those kind of signals, CH signals. You can see this one is a CH signal. It's very interesting. You can see they have a 2-stage combustion. First stage is coming from the 24 milliseconds. That's corresponding to the ignition of homogeneous from those kind of volatile matter. Volatile matter, they will generate have some methane, hydrogen, CO, and some big molecules. Then they can burn out. The signal appear again, those corresponding to the ignite heterogeneous ignition of those charts. So that's very interesting. And then if you see, this is from the lignite, it's very high content of volatile matter. If you have a bitumen miners, you see this is not so easy to see the two peaks. They combine together. So the char burnout, char combustion and the heterogeneous combustion under those homogeneous volatile matter is a similar thing. But if you switch from those nitrogen gas to ammonia, ammonia will improve the ignition way. Original is 28 milliseconds, but now you can see just at 16 milliseconds it was burned, right? It was ignited. But the burnout time was extended. But here you can still see this part, but this one was already quenched. So when you compare with the totally, you will see this different coal type: lignite, bitumen miners, sub-bitumen miners, anthracite. When you switch from nitrogen to ammonia, you can see all the coal ignition time was reduced, right? The ignition actually was how to say, the time was shorted. But if you compare with different particle size, from here, because big particle size, they will have a little bit more amount of the volatile matter. So it seems a little bit change, but not big difference. Then we normalize those signal. You can see from those lignite, they have those kind of double peak. If you're seeing ammonia, the bitumen miners also have this kind of double type shape. That means volatile matter, homogeneous ignition, and the char ignition was separate. So the ammonia can be active like volatile matter. So the ignition time, we use this kind of a line shape to fit the exact. You can see the ignition data was shorted by both of those type of the coal. But the burnout of the char, you can see, was really extended. That means it's difficult to burn out. Then we're thinking, oh, how to mix those ammonia with the coal. You can mix with the coal together in the primary air, or you can insert into different injection nozzle. We define as premix mode or stage mode. Premix mode means we mix coal together into this high temperature reaction zone. So you can see when we inject ammonia, the NO was quite quickly increase around 1,000 ppm if you just insert those kind of ammonia into those environment. Then we think, oh, we can use the air staging mode. The ammonia is still in the center. The air stage is 30% go to the downstream. That's a typical way to control NOx for normal coal combustion. But you can see NOx can be controlled a little bit, but still very high. Then we're thinking, oh, we can put those ammonia downstream, not together with the coal. You can see, oh, if the temperature was good, the position was good, the NO can be quite quickly reduced because they can simultaneously have the SNCR reaction to reduce NOx. So you can have a chance to reduce those NO emission. So you can see if you can compare with different mixing ratio from 1% to 50%. Carbon dioxide was reduced. NOx has some optimal and when with increasing, still keep increased. The ammonia was, if in some case not good, they will have some leakage. But unborn carbon was reduced. Compare with temperature from 800 degrees C to 1200 degrees C, you can see with the increased temperature, the CO was decreased. The NOx was unluckily increased. The ammonia leakage, if the temperature was high, will have a well burnout. So from the fuel NOx convert to the NO or nitrogen, you can see during ammonia combustion, more than 98 or 99% of those nitrogen actually they go to nitrogen. So you can see if you burn with those kind of coal, you can see premix mode and stage mode. When you use stage mode, you have a chance to reduce the NOx emission much even lower than the coal baseline. But unluckily, you will observe the increase of because the thing is, when you burn ammonia, there will be much higher content of moisture in the flue gas. Those flue gas can react with carbon, can regenerate some hydrogen and carbon monoxide. Hydrogen can be easily consumed, but left those. Finally, we think, oh, how to realize in a real furnace, a real boiler. A boiler is a huge one. So we choose those 500 ton boiler is corresponding to a 135 megawatt electric power capacity. This type of boiler we choose one is because they have it's a tangential fired one. In original many simulation work, people just use those post treatment for NOx. That means they first calculate the temperature distribution, species, flow field, and then after running this, they use some parameters to post calculate the NOx. But for a large amount of ammonia, because both ammonia will both oxidize to generate heat, as well they will generate NOx. If you separate those two things, will be generate some errors. So what we think is that we build this kind of global mechanism. We use the finite rate eddy dissipation model to both include those oxidization and NOx formation reaction. So you can see from the reaction 1 to reaction 10 is the gas phase reactions. For the co-bonded those kind of nitrogen species, we use this model to describe both from volatile contained nitrogen go to HCN and char contained nitrogen go to NO, and as well as the heterogeneous reduction of NO by char. So you can see those kind of things can be both considered. Then we simulate several cases, maybe totally 13 cases from the pure coal case, 5% mixing, 10%, 15, 20, the maximum is 30%. And then we, with different kind of air distribution, the ammonia we have, how to say, I will show really where the ammonia was injected. So this is a primary air, actually is a coal nozzle, it's coal nozzle. Here is the air, secondary air, pure air. We put a two level of nozzle in the middle of the upper primary air and between those kind of upper secondary air nozzle. So what we do is we both into up level, low level, or both level as well. We adjustment to those kind of air distribution along with this totally burners. Firstly, we calculate the total temperature and oxygen and CO2. We compare with those existing experimental data. You can see both temperature, oxygen, CO2 is agree well. So then we think that models was good enough. Then we calculated the ammonia co-firing case. So you can see the temperature distribution from the pure coal case to the 5% to 30%. The temperature was drops because the ammonia flames adiabatic flame temperature was lower than the coal flame. So you can see the peak temperature was reduced. For the oxygen, because we injected ammonia up of those coal burners, you can see that the lower part of those furnaces, the oxygen was enriched. So that could be, how to say, can be help in some case, can avoid those corrosion about this surface. If you see the CO2 distribution, CO2 sure is percentage to those ammonia co-firing ratio. This is NO distribution. You can see with the injection of those kind of ammonia, the NOx unluckily increased. So you can see with different kind of co-firing ratio, if you don't do anything, you can see the coal case 169 ppm. With increased ammonia, the NOx can be uncontrollable, quite higher. The thing is how to control those NOx because you need above those regulations, otherwise it will be punished, right? So we compare those 30% ammonia case, the NOx level is this data 364 ppm. Then we, without changing, we just put some air here. You can see the NOx was increased quite a lot. Then we adjustment the local with some strategy to control those atmosphere. you can see we can control the NOx around 200 ppm. 200 ppm corresponding to 400 milligram per cubic meter. And then with the SCR, they have a 90% reduction efficiency, so they can match the 50%, 50 milligram, those Chinese emission standard that could be acceptable. And then you can see with different kind of coefficient ratio, through those optimization, you can see in most case, the NOx emission can be in the level around 200. That could be a possible way in the future to apply it in the real engineering, real power station. So I think finally I go to my conclusion and outlook is co-firing with ammonia in existing coal-fired power station. Way for China, especially those kind of coal-enriched country, to reduce the carbon emission intensity. Co-firing ammonia will accelerate those volatile matter release and improve the ignition, but they can consume those oxygen around the coal particles and prolong the burnout time of the coal charts. With maximum 30% of those ammonia, the NOx can be controlled at around the level of the coal combustion case. But the thing is, if you further increase those ammonia co-firing ratio, the NOx will still be a quite challenging task to do. So that's my presentation. Thank you very much. If you have many questions, thank you.
So Professor Wang gave us a very wonderful talk, and so now we can have a question and answer for a couple of questions. Yeah.
Professor Wang, thank you for your inspiring speech. I'm Mingyi from Shanghai Jiao University, but from another group, not from Professor Yang. So if my questions are silly, don't blame me. And my first question is, I saw you said you use pure ammonia and mix it with other fuel to speed up the combustion speed. How about we increase the oxygen content in the air by some methods, and use this method to increase the combustion speed. And my second question is about the coal ammonia co-firing. Like for gas burning, for pure gas burning, the pressure. The initial pressure is very important for reaction rate. How about will it also happen on coal ammonia co-firing? Will it also affect the
is burning velocity performance of economic, I will say, in the industry way. From the academic, no problem. We can see different type of methods. We can do the research, no problem. Finally, in the industry, I think they will both consider those kind of economic performance. That's no problem. How to say, the second question is for coal ammonia co-firing case, what's the influence of pressure, right? Yeah. Okay. Because in most case with normal pressure, not high pressure case, but maybe in engines and gas turbines, they pretty like high pressure one to improve the power output. If you increase the pressure, I think the burning velocity will be decreased, but the totally fuel consumption rate will be increased, because in the same volume you can input more fuel inside of that, so the output power will be increased. That's the case. As well as we found if you improve the pressure, the NOx can be a little bit decreased. That's the good news to see. Okay, thank you.
we have any other further questions?
Okay.
Thank you. Very, very interesting talk. My question relates to the one of your first slides. You mentioned Chinese program of co-firing.
Yeah.
So my question is, what will be the source of ammonia in China?
The thing is, in China, in the economic developed region, like around the coast place, there are not so much resource. But in Xinjiang, in Inner Mongolia, in the northwest part, so many deserts, so many those kind of gobi. They have so many lands. They will put PV and wind. They will generate so many green power. Now I heard they have 50% or 60% maybe cannot be consumed locally. So the thing is, the price from those renewable can be quite low, Then they can synthesize to ammonia, and then with those kind of train to transport to the east way. The local coal power station, they just co-fire with those hydrogen will be okay. So the strategy is the local coal-fired station in the northwest region, they just make the east power station we will burn with ammonia. That's the way. Not thinking we export from the outside. I think the locally they can have quite a lot of those kind of resource. Okay, thank you.
The time limited, so we now end the question and answer sections. So we also thank our speaker again, and then we have a certificate ceremony.
Oh, okay, thank you.
Take it for you.
Okay, thank you very much. Okay.
Yeah.
Okay.
Thank you.
Thank you.
Next lecture is from our invited speaker, Dr. Vinod Giri, and for the ammonia pathway to a sustainable energy future.
谢谢。
Putting this no, this is for the live.
It's for microphone.
It's not. So.
稍微等一下，看一下照片啊，稍微等。Okay, wait a minute, so we just.
拿一下您。Nobody can tell.
好，谢谢。播放一下。播放。
No, this.
Oh, you have to speak. So, all right. Good afternoon, everyone. My name is Vinod Giri, and I'm standing alone there, but there are a few people I should mention. And Christine is sitting in the audience, and Fabian Maus, Krishna Shrestha, and there is a PhD from KAUST, Ghani Isai. These are the people keeping my energy alive, dealing with ammonia. So I was contacted by the organizer to just give an invited talk a few days back, and then basically I put this title, and then I realized hearing those beautiful talks, and especially from Christine, that I think I'm not correct stating that it, right? So if you heard her talk, then you realize probably you'll put a question mark in there, rather than saying that, okay, ammonia is basically a transition to sustainable future. So anyway, so thanks for coming to my talk. So being a chemist, I would like to start with a simple periodic table. So you have tons of elements in here. My interest is to, analyze whether these elements are to be a fuel. So the criteria being 10 kilojoule per gram. So you burn 1 gram, you want to get 10 kilojoule of the energy, because you don't, if you think about passenger vehicle, then you have the fuel, okay? So what you got from the conventional fuel is basically 45 kilojoule per gram. So that is my constraint. If you put that constraint, actually all the elements from the actinide and lanthanide series will just fall apart, and these are the elements remaining in the periodic table. And then you don't want to burn something that is very toxic. That's one thing. The next thing is that you don't want to burn something that actually comes out from your tailpipe as a solid. So that you don't want. And if you put another constant, so these are the elements that are gone, and you are basically left with hydrogen and carbon, and it is hydrocarbons, right? So that's why we are very obsessed with the hydrocarbons. So you want to continue to burn the liquid fuel. So, and the reason being that you are actually topping the table like diesel, gasoline, they are really good in terms of energy, and that's why you like to keep on burning those fuels. So if you look into the numbers now, you are burning basically 10 million barrels a day, right? So if you put that into perspective, actually $70 a barrel, so that's the fuel price currently in the market. So that is the money that is flowing in the market. It's the trillions of dollars, right? And then basically you're spending $315 a person per year, so that's a huge amount of money. Trillions of dollars is flowing in the market. There are politics, global politics, so on and so forth. That's why we keep burning fossil fuels. So if you do that, so I think we have some Chinese colleagues sitting in here. I'm not offending you guys, just bringing this chart in here. But if you look into the chart, you're actually dumping 38 billions of tons of CO2 in the atmosphere. So that's every year. If you look back, around 2000, that's just half. So we are sitting at about 421 ppm in the atmosphere. As you know, carbon dioxide doesn't like to move. It's like a bathtub. It drains eventually, but very slowly, right? So that's what it is. And then you are basically 421 ppm, and then basically China is topping the list. Just dumping 30% of the global emission is there. But you can argue that you should actually go for per capita, and I believe in that. So US being the second. So these are the scenario in here. We are burning a lot of those fossil fuels, dumping a lot of those CO2. The consequence is that I'm born in Nepal, living in Canada, and then working in Germany. So I'm a completed guy, right? So, but these pictures I'm taking from Nepal, and Nepal is actually bordering to China, right, in Tibetan area, and we have actually tallest mountains in Nepal, luckily. And then what is happening in Nepal? Like if you see Nepal back in 1980s, so these are the lap of the mountain. They are basically covered with snow, glaciers. Now they have converted completely into the lakes, and then. So those are the consequences in there. I'm just showing you some of the aerial pictures recently taken in there. And then if you talk about the temperature rise in those regions, it is already 1.5 degree above from the industrial era, right? We talk about the 1.5 degree rise, it is not uniform. If you talk about the polar region, if you reach 1.5, in some region there will be probably 4 degrees Celsius. And in those mountains, those temperature rise are going to go higher, and it continues doing that. And if you see, so basically what you're seeing in here is that glacier number is actually increasing. That means they are recessing, they are separating from each other. But if you see the mass, it is continually going down. And if it continues like this, then by the end of the century, we are done with these mountains. There will be no snow. And these mountains are feeding billions of population down south, that is India, right? And then we have problems like feeding them, right? Because of irrigation, they don't have anything to irrigate their land. So that's really a pain in there. And then if you talk about Canada, and then basically BC, we have we have hundreds of lakes, hundreds of glaciers converted into lakes. So if you heard in the news last year, like there was salmon fish actually moving towards the north, just catching the cold, cannot survive beyond 20-21 degrees Celsius, and they are actually building some some skin disease because of temperature, and they are trying to catch cold temperature and moving towards the north, and then basically they are dying on their way. And it is basically hard trenching, and you literally cry, your heart literally cries because of these temperature rise in those rivers. So again, from Nepal, so this is the recent flood few years back, and then this is the village before the flood happened, just a few, and then basically from those, Mount Everest region, one glacier lake basically burst, and then whole, population is gone, and then basically those villages completely swept away. So having said that, I'm not blaming China, okay? We are all doing emitting CO2 in the atmosphere. So we should think about that. So this is another picture like from Nepal, like never happened. I never heard in 95. Story continues if you globally tons of can my story continues on. So now the question is that if you look into the population, so I was talking to a colleague, so what we are going to do with the population, right? Every 10 years we have 1 billion, and then we cannot educate some people that we can limit the kids after 2 or 3. So we don't need 8 kids or 10 kids just to continue our race. So even though you do actually the forecast, medium population forecast, so that's the amount of energy that you need by 2050, and then basically that will multiply by 2 by 2080. So one challenge, how to feed them. The other challenge is that where you are going to get the energy, right? So you keep on burning fossil fuels and dumping CO2 into the atmosphere. So those are the questions that we have in the mind, and you have heard beautiful stories, beautiful talk, during those conferences. So I'm bringing one perspective where we talk about the electrifying those, transportation sector. And then China is doing great in terms of, installing so many gigafactories. So in 2018, that was the projection that, will be able to produce about 1.1 terawatt hour of batteries. Now the scenario has changed, and they are putting a lot of money. Look like they are actually investing almost like $200 billion into these, battery industry, and then trying to actually attain about 4 terawatt hour. And if we attain that 2050, the projection is that we can actually double. That means 10 terawatt hour. If you put all these numbers, and let's say we power the vehicles, passenger vehicles. That is the amount of batteries you would need. If you put all these batteries to just drive the passenger vehicles, that is how much you can do. 200 millions out of 2 billions. And then how we are going to actually electrify. And the another question is that even though you want to electrify all those vehicles, do we have the resources? Do you have the the metals? Do we have the alkaline earth metals, transition metals? The question is that we don't know the reserves yet. We don't have those resources, so we cannot do that. So even though in good scenario you have basically you'll be able to do just 33, and rest has to come from somewhere else, right? So that is the scenario we got in here. And then so this is the slide I took from Heinz Spies. He did that in 2024 in the hotel lecture, and it shows that even though you push hard in this scenario, so that is the best scenario you can think of. Even in that scenario, you'll be burning actually 40% and more, and the coal is still going to be there. Natural gas is going to be there. Oil is going to be there, and the shear is going to be more than 40%. So we'll be still continue burning hydrocarbon fuels. So now the question comes: can we actually? We know this fuel ammonia. And then as a fertilizer, you can argue, no, we need to feed more people. So we'll utilize ammonia just to make more fertilizers, because we need to feed, 10 more or 20, 10 billions people or more. So another way to see is that can we do that in terms of fuel, in terms of carrier or something like that, right? So that is that is where I'm taking you. And it is hard to engage you, because you have heard so many stories, and ammonia is a small molecule. How big you can make? So I cannot make a bigger story than this, okay? So if you look as ammonia as a hydrogen carrier, that is where the ammonia is sitting. It can carry double the volume of actual liquid hydrogen. It is just great in terms of carrying the hydrogen, right? And then basically long transport, it will really do good. So Now, the question is that once you actually sequester hydrogen in terms of ammonia, how do you get back hydrogen? So that's the biggest question. And then the cracking of ammonia, how energy intensive is that, and this and that. So those are the questions that we have. Actually, some people are working in the catalyst sector, and they are actually working in that direction. So my idea is that this is just my question, right? If you get into this topic, please remember me. But I'm just bringing Dr. Murray Thompson. So he's actually cracking actually methane and then basically you release hydrogen, carbon, you dump it down, and you utilize that carbon for something else. And he says that microwave cracking is really great. You can actually save 80% of electricity. So they have built Aurora hydrogen that is operating in my province in Alberta. So that is doing great. So my idea is that if ammonia does this, if methane does this, ammonia is basically microwave active. So you can actually just pump the energy, microwave energy, into ammonia and crack. I think it will do a better job than methane cracking, and we can actually save a lot of energy. If somebody in the industry or the researchers are doing that, please remember me cracking ammonia in the microwave reactor. Okay. So this is one idea. So, but our idea is that why don't you use ammonia as a fuel? And basically, this is the slide from Christine, and she likes to show the slide every time she talks, and I really love it. So you already heard that, we know this ammonia as a transportation fuel back in 1940 when we were World War. We don't have any fuel, so that's why they need to drive their bus with the ammonia-driven, fuel. So it continues, and we have the passenger car in 2015, and Christine just told that Toyota is actually built already the ammonia-driven engine, and that is already in the market, and the CEO is saying that probably it is end of EVs vehicles. So we just need to see if that is the case. So this is about the history. And on our side, what we are doing is that, if you want to use ammonia in the transportation vehicles, passenger vehicles, then we need to do something. That is ammonia, and it is very stubborn. It is reluctant to react. This is DME, like a diesel fuel. You need to push that curve right there. And that's what we did, push this curve towards your right, and then this is the different blends. And if you go 50% of DME, that actually reacts just like the diesel fuel. And then if you compare with the phase fuel, that the gasoline fuel, that actually the ignition behavior is similar to that of phase fuel. So 10% of DME with ammonia, that mimics the characteristic of gasoline fuel. So I put some numbers together. Estimated run is great, and then octane sensitivity is 12. That means you don't expect to see any NDC behavior because the octane sensitivity is more than 10 or 8. So that's why the line is pretty much flat. So if you put the numbers together, and then you can argue with those numbers that I calculated just yesterday. So gasoline would cost $1.27 a kilogram, and if you have the gasoline type of blend ammonia DME 18% to 82. That's the money you are going to put per kilogram. And in diesel side, this is going to be 80 cents per kilogram, and diesel in the market would cost 1.13. Cost-wise also, it is actually helping, right? But in terms of energy, you can argue. So it might go a little higher than that. So this is the area we are working, and then if you look back in the literature, this is Pino Savia from Mara group, and you can see there are so many models in here, and then basically they are not going to describe those ignition properties of ammonia. So this is just ammonia burning. Here is the hydrogen evolution, and if you talk about the NO, actually their non-monotonic behavior of NO is not, actually they were not able to catch that. So that is basically some chemistry is missing in there. And then there are several of those reactions. Some of the reaction is Stagny. His group are actually working to actually derive some rate coefficients for these reactions. So we understand the chemistry now better. And so whenever we talk about the model, and there are some people like Glarberg and Alexander Konov is sitting in the audience, so we need to actually recognize these guys and their way of teaching us to understand the nitrogen chemistry. So anyway, the story continues on. So this is just a recent paper from Wang with Peter Glarber. As you can see, you can even not understand HONO, and where the HONO is coming, no model currently available in the market is able to do that, right? So these are the areas that we need to look on. And then Fabian Maus group, they started looking into the ammonia mechanism, and they published the first paper in 2018. And then later on I came in and then basically put some carbon species. Now we have built all four, and then recently we are doing with Christine, building the mechanism, and then basically looking into the alcohols and so on and so forth. That is submitted in combustion and flame with the improved model with the predictions. And as you can see with that model, the non-monotonic behavior of these NO from Sabia, we were able to catch roughly. And then NOx sensitization, we were able to catch the mole fraction of this fuel. And then here NO we were able to catch. So this is a decent job in order to capture those behavior of those species. And these are again beautiful experimental data from Christine's lab. And we tried several models in here. As you can see, that was even worse than anything else in the market. But we had to work a lot in order to improve the mechanism. And this is the mechanism that is updated, and we are comparing with the other people. But when you are writing your mechanism and claiming yourself, just try to recognize some people who did actually those early understanding of nitrogen chemistry, and that includes the expert like Konov, Alexander Konov, and Maria is sitting there, and there are other people like Peter Glarber. So you change some reactions and you call this model. This is going to be scientifically not correct, okay? So yeah, we can claim anything, but we need to acknowledge these people. So anyway, so we are comparing some data in here, and then our model is doing a little better than the other, characterizing this. This is for neat ammonia, and we blended with methanol, and our model is doing better than the other model out in the literature. And it is ethanol is still a problem. We cannot catch the ignition behavior of if you mix ammonia with ethanol. So there is a little difficulty. Probably we don't understand the interaction chemistry very well yet. So that is submitted in with Christine in combustion and flame. And then probably I'm just talking a little faster. So anyway, so here, so we are working with some people from Duisburg, Essen, and with the Atakan group, and they actually deliver us very beautiful data. That's the time of flight, mass spec coupled with the flow reactor. And these are the species profile. As you can see, this is the methanol profile as a function of different methanol concentration. Here I am showing the hydrogen evolution, and here the formaldehyde. If you dump anything, you will end up having the formaldehyde in the system, and methanol does produce a lot of formaldehyde. As you can see, I'm comparing again the chain model 2023 and Labadera, Wang 2024, and this model, updated model from system from 2022. And as you can see, our model is actually able to characterize the onset of reactions for methanol going away as a function of temperature. These models are not doing great just because there are missing chemistry, CN chemistry, and then Wang model, he has that in there, so that's why it is doing a little better job. So we are able to characterize those chemistry of ammonia mixed with methanol in different phi. And here you can see we still have issues, and I talked that already in my other talk. We still have issues like capturing those hydrogen evolution at higher phi. So that is the issue in there, and still we have some issues with capturing those formaldehyde. And then basically only these two models, basically Wang and ours, is able to have that little blip, but it is not capturing that. That being said, that we still need to work on the modeling aspect, trying to understand the chemistry and putting the information together. So NOx is another issue that we got to deal with that, and you don't want to see N2 a lot in the atmosphere. I told you, even though you have 2 ppm N2 release into the atmosphere, that is as bad as having 420 ppm of CO2. So you need to understand how I'm doing with the N2O for different blends of methanol and ethanol. I'm just showing you an example here, mixing ammonia with 5% ethanol and 10% ethanol in there. So basically, it's just a simple, very attempt doing this simulation in a constant pressure reactor. As you can see, if you increase the pressure, the ammonia actually the N2O is pushed down towards the lower temperature. And if you blend just 5% of ethanol, these islands are completely gone. So basically, you're not producing it. You have seen that in other talks that N2O, if you burn really a little rich and blending with these oxygenate, you don't actually get a lot of N2O. And our modeling is actually showing that. If you increase the pressure, it does so pressure dependent, and it is completely gone. Here it is a little dot in there, but you can actually just tailor the things so that you don't get any N2O from the system burning with ethanol and methanol. And if you talk with any engine expert, they would say that what kind of fuel you would like to have down the road, and they will always say methanol. And methanol is a great fuel, and that's the reason we are doing just ammonia and methanol. So anyway, actually concludes my talk, and basically I've listed some of the points in here. So what we saw is that ethers and alcohols are really great to promote the combustion behavior of ammonia. So proper tailoring is needed in order to have the desired characteristic of the combustion behavior. And then basically kinetic model, we have developed that, and that is validated against several experimental targets, and new targets had been the high pressure Flemish speed data from Christine lab, and we are actually doing a decent job capturing those data. And then so what we have seen is that, like, if you blend oxygenate with ammonia, and then basically you can suppress a lot of NOx. So NO and N2O, and then one example I just showed you before. With that, I conclude my talk, and I thank you for your attention. If you have any questions, please. Yeah, thanks.
For this with the limited time, we have only one shot questions.
Thank you very much for the nice talk. Here's Boshu from the PDP Germany. So my question is, like, as an experimentalist, so I believe more my data than my model. And as a modeler, you believe your model more than the others' data, maybe. So the question is, how can we evaluate the experiment data all over the world? So, we can see data we have obtained from different institutions could be all nice. Yeah, but somehow our model can only agree to certain part of them. So do you have a suggestion in this?
Yeah, like you got a beautiful question, but what we do is that we don't want to sneak. We don't want to sneak your data. I know your data, and then you are saying you're claiming you're a mentalist. I am too. And there is Christian sitting in the audience, and we have the data from our lab also, So it's not that, we are just taking the literature data and trying to validate something and trying to claim something. If you see that paper, we have taken the data from Ravi Fernandez lab, the data from the other people, starting from ammonia, blend with hydrogen, and we are actually evolving with time, not that claiming something that is not right. So we are not tricking you guys, we are not sneaking, so we are actually testing a lot of those data.
No, for sure, I also see like this way. Just my question is, how can we strengthen our community? Yeah, we also have people together with all of these colleagues here.
Yeah.
We have review paper, we have collaboration paper.
Yeah.
But somehow this year in Milan, we also have RCM workshop, we have blend workshop. So how should we work together to make data together? Yeah, to compare to each other. And in some data, we can say, okay, we trust our data in the community, and we trust the chemistry community. So that may be something we can discuss later, but I just
So realizing that, so we are connecting to PTB, to your boss, Ravi Fernandez. So we have some DFG projects, so that probably kicks in. So we are working together just to make you happy. So yeah, thank you. Anyway, so this, yeah.
We have for the final hearing.
Yeah, thank you.
Thank you. Yeah.